Most of the time we are unaware of the massive amount of atmospheric pressure bearing down on us, because that pressure pushes down evenly on us from all sides, even from inside our lungs. Since our bodies are mostly composed of water which cannot compress, we don't feel atmospheric pressure changes unless air is trapped in our ears or our lungs. The garbage bag is filled with air as the student steps into it. The air pressure inside the bag is at first equal to the air pressure outside the bag, so the bag won't collapse in on the student until we reduce the pressure inside the bag. With the student inside the bag, the weight of the atmospheric pressure will soon be felt as the pressure inside the bag drops. It seems like we're sucking air out of the bag, but scientifically speaking, we're just reducing the internal pressure of the bag. The student inside the bag begins to feel the outside pressure bearing down on them when there's less pressure inside the bag pushing back. When the pressure inside the bag is at its lowest point, the student gets a strong sensation of the actual weight of atmospheric pressure. Most kids thought this was pretty funny.
This is the vacuum chamber, and this is the pump that will pump air out of the vacuum chamber, and it shows a lot of principles of the atmosphere. This is a pump from a recycled refrigerator, and the gauge shows how much air is being pumped out of the vacuum chamber. For our first experiment, we're gonna put a sealed Dorito bag inside the vacuum chamber and see what happens. First, we're gonna close the valve to turn off any air coming in. Then we're gonna flip the switch to power up the pump. The gauge is gonna show how much air is being drawn out of the vacuum. We expect it to draw 22 inches of mercury. As long as there's a vacuum in here, we can't open the chamber. Once we let air back into the chamber, it will be a simple matter to open it. Now we can open the vacuum chamber and enjoy our bag of Doritos.
What we have here are two ping pong balls that are almost perfectly balanced. This ping pong ball has a hole in it. This ping pong ball does not have a hole in it. To see what will happen to these two ping pong balls when we seal the vacuum chamber. We close up the valve, and now we're going to power up the pump. Once the vacuum chamber has taken out all the air, the ball without the hole is heavier than the ball with the hole.
I'm going to squeeze the bottle and get as much air out as I can, and then I'm going to tighten the cap. So now we're going to take this crushed water bottle and this inflated balloon and put them in the vacuum chamber, and we're going to see what happens. Whoa. Ah. So now we're going to let the air back in the vacuum chamber. We're going to see what happens to the water bottle. There's no hope for the balloon.
For this experiment, I'm going to fill this little container half full with shaving cream and then put a narrow nozzle on it. Shaving cream has thousands of tiny bubbles in it, so when we put this container in the vacuum chamber, the shaving cream should expand. When we return the air into the vacuum chamber, everything will collapse.
We did an experiment where we spun a top without turning the vacuum chamber on. What we discovered was that when the top was spinning in the vacuum chamber, it spun for about 20% longer. It spun for longer because there was no air resistance in the chamber.
These are just a few of the experiments that you can do with a vacuum chamber.